Welcome back. In previous lecture, we talked about flow of hydraulic fluid and we discussed about volumetric, mass and velocity of flow. Then we identified the main two parameters that impact the flow of any fluid, which are viscosity, and we have high viscosity and low viscosity, and flow state, which is turbulence or laminar flow. Also, at the end of the previous lecture, we demonstrated an example on how to calculate the distance moved by a piston when a force applied to an enclosed system. In this lecture, we will talk about the relationship between force, pressure, flow, and speed combined together. So let's start with lecture number 5, hydraulic fluid characteristics. This will be the last part in this topic. Here we have three scenarios to check the relationship between force, pressure, flow, and speed on a moving piston. The first case here we have a system where raising a load, the second one lowering a load, and the third one to have both valves opened. It should be noted that pressure in a cylinder is determined slowly by the load and the piston area in a steady state. If you remember, we have P equal F over A. And it is not dependent on the velocity of piston once a constant speed has been achieved. In this sketch, we have two valves, one at the inlet and one at the outlet, and enclosed cylinder with a piston carrying a load. Fluid is delivered to a cylinder at a rate of Q, centimeter cube per second, and once the inlet valve is opened, a pressure spike is observed as the load accelerates, but the pressure then settles back to a steady value of P equal F over A, where A is the area of the piston in centimeter square and F is measured in kilogram force. The load rises. This load will rise with a velocity of V, which is equal Q over A, centimeter per second, and the velocity can obviously be controlled by adjusting the flow rate. And to adjust the flow rate, you will play with the inlet valve openings. So once we have the inlet valve opened, the fluid will run through the cylinder and then it will start raising this load up, considering that this outlet valve is closed. On the other side, if I want to lower this load, the inlet valve is now closed, so there is no supply, and the outlet valve is now open, allowing the return flow to go back at a rate of R to flow out of the cylinder. Here, once I open also the outlet valve, there is a spike in pressure, negative in this time, as the load accelerates downwards, but the pressure reverts to P equal F over A once the steady speed of V, which is equal R over A, is achieved. So R here stands for the flow rate exiting the cylinder. Now, the last scenario here, I have both valves are opened, the inlet valve and the outlet valve. So when the both valves are open, the net flow is the difference between the inlet and the outlet, which is Q minus R, giving a cylinder velocity of Q minus R over A, which can be positive in case of rising or negative in case of falling, and this purely dependent on which flow is largest. Example, if I have the flow entering the system is higher than the flow exiting the system, then this difference will lead to the piston or load to raise up because the inlet is more than the outlet. On the otherwise, if the outlet flow rate is higher than the inlet flow rate, then I'm expecting the piston and load to fall and go down because the outlet flow rate is higher than the inlet flow rate. So The steady state pressure, however, is unchanged at a value of P equal F over A. These are the three cases we demonstrated to understand the relationship between force, pressure, flow, and speed, and which will be the basis to control any hydraulic system. We came to the end of this lecture. Thank you, and see you next lecture.